Hello and welcome to another video. In this video we're going to be working on kth smallest in lexicographical order. And in this one you're given two integers n and k, and you want to return the kth lexicographically smallest integer in the range 1 to n. So in this is like this, and this is the same thing as yesterday, like the lexicographical order. So I definitely recommend doing yesterday's problem to get a better understanding of how you can get the next number in that, because I'm not going to spend too much time on that. But essentially I talked about this yesterday, where if you have some number, x, the next smallest number, lexicographically, is just adding a 0 to the end. So that's why 1, we have 1, 0, and then if n was like really big, it would be like 1, then 10, then 100, and so on. Yeah. And then if you can't add a 0, I talked about this yesterday as well, the best thing to do, or if you can't multiply by 10, the next best thing to do is just add a 1 to the number. So that's kind of what you have here. So you multiply by 10 when you can, if you can't, add a 1. And that's going to be the idea of this problem. Okay. So in this case, the second smallest is 10. In second example, n is 1, k is 1, so just 1. And I also said in previous videos that constraints are really important. So here, you can look at the constraints and you can know immediately, like, I can't just get every number because it'll take too long. So if you use yesterday's solution, where we basically generated all of these, it would take too long because 10 to the 9th, like, you have to do better than linear. And the way to figure out to do better than linear is also pretty hard in my opinion, but I'll try to explain it. So basically the idea is we kind of know how, like, what transition states we can have for our numbers. And we're basically going to go down a tree and figure out digit by digit what we want. So for these types of problems where you're trying to figure out, like, you have some numbers that are continuous, or like a multiplication table that's continuous, and I want like the kth biggest, you want to figure out a way how to traverse that efficiently and just figure out, like, okay, given this small part, do I have enough numbers, and which way do I have to go? Because I can't actually make these things. So that's kind of the idea here. So basically what we're going to do here is we're going to have a tree, but we're not going to have a tree. We're just going to have a number. I'm just going to show it as a tree. And so the tree will have a root, and every layer will be like what digit it's going to have. So basically, like, the first digit can be, like, let's say we have 13 in this example. So the first digit can be a 1 or a 2 or a 3, and so on and so on and so on and so on. And for each one of these starting digits, you can have subdigits, right? So for a 1, you can have a 0, 1, 2, 3. And then for 2, you can't actually have any subdigits because you can't have like 20. So yeah, so this would basically be the whole tree. So it would be like 1 to 9, and then the 1 would have these, and then everything else wouldn't have any of these. And the basic idea is what we're going to try to do is we're going to start at 1, and we're just going to say, like, so we can either traverse down to get more digits and say 1 is our starting digit, or 1 is not our starting digits, and we're going to traverse to the right. Yeah. And the way to figure that out is basically, we know for sure that all of these, right, because in a lexicographically smallest string, when you have a bunch of starting characters, like when you have a bunch of numbers on a level, everything in this left subtree is going to come before this subtree, before this subtree, and so on. So the idea is we're going to say, like, for this subtree, can we calculate how many nodes this subtree has? And then we know what k is, so we can figure out, like let's say the subtree has like 5 nodes, but k is like 8. Then we know that we have to move on to the next subtree. And so the idea is we're going to do one of two things. We're either going to go down in the tree or go to the right. And every level can have at most like 10 nodes, I guess. Yeah. So we're for sure going to eventually get a solution. We're never going to, like, go out of bounds or anything. And so what this would work, the way this would work basically is we'd say, okay, well, this has 5 nodes and k is 2. So that means that this answer has to be in here. And if it wasn't in here, then we could say, like, let's move on here and let's subtract. Like, if we know there's like 5 nodes in here, then we can subtract 5 from k, because these are, like, we've already looked at these. So now we can look at different stuff, and we can subtract from k. And we're basically going to keep traversing and subtracting from k until we hit the thing we want. But in this case, because k is 2, so we're going to do this. We're going to get a result of 5. And also the thing, we're going to make a slight adjustment. So we're going to index k to be like the index number that we want. So instead of like k being 2, we're going to say like the 0th number, the first number, the second number, and so on. So we're going to make k equal to k minus 1. So we'll say k equals 1. And then if we find 5 nodes in here, that means that's bigger than k. That means k has to be in here. And we're basically going to keep doing this until k is 0, because if k is 0, that's basically the number we want. So k is not 0 here. So that means that this tree is big enough to hold k. So we can just say, okay, we know for sure this first number has to be a 1. And then we can traverse down to the next level just by multiplying by 10. And remember I said if you have a number x, the number after that number will be that number multiplied by 10. So if we traverse like that, that means we traversed one number down. So now k will be 0. And because k is 0, we'll just return this number. And this is 10. So we're not actually going to build this tree. We're just basically going to build this number in place, and it will represent the tree. Let's take a look at one more example to demonstrate this a little bit better. Let's get rid of all this. So let's say our number is like, let's try to figure out a number where it's not going to be in the first part of the tree this time. Hopefully, at least. Yeah, I guess let's say we have like 34. And k is like 15 or something. I think hopefully that works. So same kind of idea. We're going to have a root. And the first number can either be 1, 2, or 3. It can technically be more. Like, we're going to technically have a tree with more, but we're never going to traverse past n. So the first number has to be 1, 2, or 3 for 34. And then for 1, this can have a 0 through 9. So I'm just going to represent it like this, 0 through 9. And then 2 can also be 0 through 9. Right, because 29 is fine. So, and then 3 can have 0 through 4. Okay, so we're going to start here, same thing. And we're going to decrement k because, like I said, we want k to be like the 0 index. So instead of the 15th, we'll take the 14th smallest. So first thing we're going to do is we're going to look at this tree and calculate how many numbers there are. And let me explain that a little bit better, how we're going to do that. So the way to calculate every level, how many numbers there are, like in this tree, we're going to go down level by level, and we're going to count how many nodes there are on the level, but you can't count them in linear time. You have to do them in O of 1. And so the way to do them in O of 1 is we can just take whatever number we're at, we can take the next number, and then subtract the next number from this number to know the difference. So I'll kind of show why that makes sense. So basically, in this function that we're going to write, we're going to have our current number, which will be 1, and we're going to have our next number, which will be 2. And so for this level, the number of nodes in the tree is just going to be next minus, it's actually going to be the minimum of next minus current, or, yeah, I think it's the minimum next minus current, or the n minus current plus 1. And I'll kind of show why that is. So basically in this level, next is 2, current is 1. So in this level, we have 1 node in our tree. So we have 1. Then we take both of our levels, our next and our current, and multiply by 10 because we want to go to the next level. So we want to go to here and here. So cur becomes 10. Oops, 10. And next becomes 20. And how many nodes are there in this level? So it's either going to be 20 minus 10 or 34 minus 10, whichever one's smaller. And so 20 minus 10 is smaller, so there are 10 nodes in this level, right? 10 through 19. So there's 10 nodes in this level, so we'll add 10 here. Now multiply again. And we keep doing this until our current number is no longer smaller than n. So when cur is 100, there's nothing here, so we're done. So there are 1 plus 10 nodes in this subtree, which is 11. So hopefully that makes sense. Why I use this next is because the nodes in your current tree, this level is going to be the level of the next tree minus this. So if this is 20 minus 10, that's how many nodes are in here. And if this is like 200 minus 100, that's how many nodes are in this, and so on and so on and so on. But if this was 200 and this was 100 and n was 134, let's say, or 150 or something, then there would actually only be 50. So that's why you also compare this as well. And so in this level, there is 11 nodes, but k is 14. So that means that if there's only 11 nodes here, then k has to be not in this one. We have to keep going. So we're just going to, instead of moving down, we're going to move to the next level here. And we're going to say we look through 11 nodes. That means we're going to subtract 11 nodes. So now k is 3. So we're going to look in here. And as you can see from this picture, there's also 11 nodes in here. So this whole thing is going to be the same thing. We're going to get like 1 in this level, 10 in this level. So there's 11 nodes in here and k is 3. So that means k has to be in here. So if k has to be in here, we will take our current number multiplied by 10 and subtract 1 from k. Because like I said, the next number of 2 is 20. So we'll get 2. And then for this subtree, we're going to calculate how many nodes there are. And there's only one node. So if there's one node and k is 2, that means it can't be this node. So we will subtract and go to the next one. And so the next one will be a 1, right? It'll be like 20, 21, and then we'll do the same thing. So for 1, we're going to calculate how many nodes there are, and there's 1, and k is 1. But remember, k is 0 index, so it's not in here either, so k is 0. And then we'll go to the next one, which will be 22. And then there will be one node in here, and k is 0. Or actually, we're going to be technically done because we'll go here, and then k will be 0, and then we'll be done. So we will return 22. And if we actually write out for this n equals 34, if we just write out these numbers, let's see if we did that correctly. So I believe k is 15. So let's write out these numbers. So it's going to be like 1, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 2, 20, 21, 22. So how many is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so 22 is the 15th smallest number. So hopefully that makes sense. We're basically going to count up a function to calculate how many nodes there are in a subtree. And then we're either going to traverse down further into that subtree if that subtree has our k value, or go to the next one. Yeah, definitely a very tough problem in my opinion. Hard to understand. And probably hard to code if you've never seen it before, and hard to code if you haven't seen yesterday's. So this would be a pretty ridiculous interview question, I think. But yeah. But the general thing with these problems, the main thing to recognize with these problems is I can't do linear. I have to figure out some way to try, like, to jump to series of numbers and figure out, is my number in that range? So this same kind of thing is in like a multiplication table or a bunch of other things. You basically have to figure out some pattern. You say, like, if I go to some spot like here, is my number in this thing, or is it in this thing or something? You have to figure out some kind of shortcut. Okay. So we're going to subtract from k, like I said, because we're going to make k 0 indexed. We'll make our current number 1. And we'll say while k is greater than 0. If k is 0, that's the number we want, so we're done. So we want to calculate how many nodes are in the current subtree of the number we're at. So we can say, like, int count equals, let's just call it like count nodes or something. Yeah. And we'll pass in our current number and n. We'll write this last, and then we'll say if the count, actually, let's think. So if k is greater than or equal to count, so if there's 5 nodes, remember k is 0 index. So if k is 5, we want k to be 0. So there aren't enough nodes here. So we can say, like, if k is greater or equal to count, then it's not in this subtree, so we move on to the next subtree, and to move on to the next subtree, we just add 1 to our current number. And we subtract the number of nodes we've seen in this subtree. Otherwise, we move down our current subtree, so, and we subtract 1. And we might have some issues with ints and longs here. We'll double check. Yeah. So maybe, I guess what we could do, just make everything a long again, and then just return an int at the very end. Sure. Okay. And so now we have to write, so we can say like return int cur. Now we have to write this count nodes. So private long count nodes. And it's going to take in int cur, int n. So like I said, the way to figure out the nodes at the current level is just to figure out how many nodes are at the next level. So we can say like int next node equals cur plus 1. And we can say, and we're going to have a result. Actually, let's do long. Actually, I think this will be fine, actually. Let's do long result, maybe. Equals 0. Okay. And then, yeah, and then we can say like while cur is less than or equal to n, we'll keep checking the level. And so the number of nodes is minimum of n minus cur plus 1, right? Like if we're on node 35 with a number 35 and n is 35, there's one node there. So that's why it's the plus 1. Or if we're on that other example, like here, like we're on 10 and the next number is 20, then it's just a straight subtraction. So this is next node. Cur. And then when we do that, we go to the next level, which is just multiplying both nodes by 10. So cur 10, next node. Might have to convert all these to long. I guess we'll see what happens. And return result. Okay. Let's see what happens. All right. Let's see. Incompatible types. Long count equals count nodes from long to int. Oh, right. So let's just make this long as well then. So make this long, make this long. Okay. Okay, there we go. Interesting, not enough submissions. Okay. So, going back here, so for time complexity, basically, when we're determining, so let's just go through step by step here. So, for every single node, we're calling count nodes. So count nodes basically goes level by level down from a node. So it will go level by level down, right? So it can start here and then it'll go like level by level. So that's log of n. And then how often does that happen? So at every single iteration, we either go forward or we go down. So going forward, like from any level, you can only go forward 9. Let's see. You can go forward a lot, actually. Yeah, it's not going to be like 9 times. Well, no, I think it will be 9 times. Because even though like this can have this huge subtree, yeah, at every level you can only go forward 9 times, I think. Because you can't change the number before. So you pick some number and then you go to its children, and its children can only be 0 to 9. So even though this subtree eventually might look like really big, you're only going to be going down like one path here. And then, yeah, you can only go forward 9 nodes. So going forward is basically constant time, and then going down is log n. So you can go down log n, and then every time you go down, you're going to call this count node. So it'll be like log n times log n, which I think is like log squared n. And then space. So this part is constant, but calling count nodes. So actually count nodes is not recursive. So this is iterative, and this is iterative. So because this is iterative, this is constant space, and this is also constant space, I think. So I think it's just like this. But yeah, definitely one of these problems, like, you might not understand from the video, you might have to like look at it again. But essentially the whole point is like, I'm calculating how many nodes are in a subtree, and then my answer is either in this subtree or in some other one, and then I can move on, and then I can basically traverse these subtrees logarithmically instead of going node by node. So even though this, like, if I drew out this whole tree, this would have, like, if you think about it for the children, this would have like n children, but we're never like building the tree. We're just going down logarithmically. So once you pick a parent node, you only go down 9 children, and you pick one of those. And then once you pick one of those, and you only go down 9 children, and so on. So it'll basically be something, or 10. So it'll basically be like 10 log n, the traversal down. But because 10 is constant, it's fine. And it's also log base 10 of n, not log base 2 of n, so it's even faster. Something else to mention. But yeah, I think that's going to be all for this one. Definitely a tough one. Hopefully it makes sense. If you have any questions, just ask in the comments. And I'll see you in the next one. Thanks for watching.